Stanford University.
We're going to be introducing something. You are here. You are making history today. This is going to be the first ever visual Oxford debate in the history of the world. It's going to be taking place right here. And I don't want to be too hyperbolic about it, but the fact is what we're going to do is we have a very interesting panel of 3 people who come from various aspects of the design engineering industry and academia, who are going to be sharing with us their thoughts on what is design and what is design thinking. And we're going to do this in the context of this visual debate. Here's the way this debate is going to operate. We have our 3 panelists. I'll be introducing them in a moment and asking them to come sit up here. The idea is 3 pretty interesting people, one by one. We will ask them to take 4, 5, 6 minutes and come up to one of the whiteboards and draw out their idea of what is design, what is good design, or what is design thinking. We gave complete free rein. This could be a methodology, this could be an approach, this could be a concept, but we want it to be something that you feel comfortable drawing, because we want to really get this sense of seeing not only that these people are smart, but they can convey their idea to you in a way that we're all going to be able to get. And I'd like now to introduce our 3 panelists. And we're going to start with the guy we have here in the room with us. You remember there's this joke, there's a guy who says, I could tell you what I do at work, but then I'd have to kill you. We have that guy in the room with us. The guy who is the official original man in black is here. And this is Mr. Gilman Louie. And Gilman, if you'd like to go ahead and take your chair, if you would, come on up. Now, just to give a little bit of background on what Gilman has been able to do, the thing that I was most excited about is, and this applies to our second speaker as well, all my life I wanted to be a fighter pilot. I am a pilot, but I never became a fighter pilot. But I always wanted to be a fighter pilot. And one of the things that taught me why I probably should never become a real fighter pilot was I played a lot of combat aircraft simulations, including Falcon. If anybody's ever played the Falcon series and Falcon 4, I'm in awe because here's the man who made it. Okay, so Gilman, thank you for joining us. Thank you. You remember I mentioned a second ago it had been one of my lifelong dreams to be a fighter pilot. We have the fighter pilot with us here. We have one of those people who really truly does have the right stuff, and that has been proven several times. If anybody was in the conference, the workshop I gave this morning, I did go on at length about the opportunities that I've had personally to interview this particular person and share some of her ideas. We have Missy Cummings. Missy, if you would go ahead and come up. Missy was one of the U.S. Navy's first women fighter pilots. And then Missy has gone on since to get a number of different degrees. Is presently Associate Professor of Aeronautics and Astronautics at MIT, and is also the director of the Humans and Automation Lab at MIT, and has several different degrees. And Missy has worked on some really fascinating instrumentation displays, and this is where I took an interest in her work and actually interviewed her, and some of this appears in the back of the napkin book. And I'm fascinated to see how Missy will be able to describe with pictures some of the things, this combination of what is it that you learn when you're landing an aircraft on an aircraft carrier, versus what is it that you learn when you're in academia, versus what is it you learn when all of those things intersect with trying to get money out of business people. So I'm very curious to see what kind of picture we will come up with there. So again, Missy, thank you. And our third panelist is Mr. Benjamin Button. How many people in here have seen the movie The Curious Case of Benjamin Button? A number of people have seen it. Well, you know, we all thought that Brad Pitt was the actor who played the character of Benjamin Button. It turns out that that's not true at all. It turns out that the real Benjamin Button is in the room with us, and it's Steve Perlman. Now, what Steve has done, you thought it was Brad Pitt. This is even better, because Steve not only was... We were hashing out this as we were standing up here before this started. Steve is the guy who invented QuickTime. Now Steve will say, oh, I was the team lead on QuickTime. Well, Steve was the guy who invented QuickTime. But that just got things started, because then we went on to inventing web TV, and this is always of interest to people in academia. Do these inventions actually have an upside? Sometimes they do. And presently you are the founder and head of Reardon Companies, an incubator for companies that focus on technology and innovation and creativity, and you've had a couple of interesting products come out of that. One is MOVA, which is the motion capture system that was used in Benjamin Button. And another one is OnLive, which I was doing some research on OnLive. Is OnLive live?
We are just about to start open beta.
Okay, that's, I thought. It's not quite OnLive yet, but it is a cloud-based online gaming system. So Steve, thank you for joining us. All right, so a couple of rules. We're going to start with Gilman. Gilman will have, and I will try my best to time this, but I'm a disaster at seeing the clock over here, so if I get behind someone else, we'll have to mark or someone will have to wave at me. Gilman, you've got 6 minutes to draw us your picture of what is good design, what is good design thinking. And ladies and gentlemen, Gilman Louie. Go for it.
Very quickly. Let me take it from a venture capitalist point of view, right? So this is a subset of design. It's about what goes through my head, both as a former entrepreneur and as a current venture capitalist. So let's start with the end. The end is money, right? So it doesn't matter whether you're trying to pitch the new stealth fighter, trying to take money out of the wallet of the Defense Department, trying to get a new idea funded, trying to get entrepreneurs to buy into your vision, trying to get a consumer to buy your product. It's about the money. It's not a perfect measure of good design, but it is a measure of design. And we start with the end, money. Okay. You have two individuals that typically goes into a room, usually in a conference room in Silicon Valley, on Sand Hill Road, and that is the VC and the entrepreneur. And the entrepreneur's job is to convince the VC to part with the money, to fund the idea, to build a great product, to get to lots of money, okay? With the promise that the VC gives me money and I will get back more money than that person gives me, and as a VC I pray I get my money back. So that's kind of how it starts off. Now, all great ideas start with something, and my view is it starts with fiction. In other words, an idea has to be based in something that tells a good story. And let me tell you why. People get confused between design and engineering. Engineering is a frontal lobe activity. It's what you think about. You have to think about engineering. It's hard work. It has all that math and science and all that other stuff involved. Design is a caveman activity, right? It's about getting people emotional. Figuring out, I really want this. So one of the things, because I come from the toy business and the video game business, I always say good ideas come from either Star Trek, or it comes from 24, when I was at CIA, or when I was in the video game business, all the things I wanted to do when I was 5, like being a fighter pilot. So, I have a friend who thinks the same way, and I'm going to give you a case study. It's a company called Smith Figure, just got announced, got $29 million to produce the next generation toys for the connected generation. So, big idea. Starts off with bug. Entrepreneur says, bug. We need a toy about bugs, because I love bugs. There hasn't been a good toy bug game. There hasn't been one. Pokemon is about monsters. Bugs are better than monsters. Okay. With bug comes, we got a team. So up comes the team. I need a marketing guy, design guy. I need somebody who actually knows something about money, because otherwise I can't get in. So, comes up to the team. That team says, okay, I'm going to put all this stuff, unfortunately, into PowerPoint, which I unfortunately have to listen to. Now, I'm listening to this PowerPoint presentation, and I'm saying to myself, what's the idea here? What's the big idea? Okay, the problem with most people is when they pitch, they give me yesterday's idea. Here's all the things that worked in the past, therefore this thing is going to work today. Here was the last big hit, this is the next big hit. Big ideas is about disrupting the future. So, what am I thinking about? I think about how to change the world. Is this idea going to change the world? Maybe there's a better way to apply this bug to change the world. So, he's thinking about bugs. I'm thinking about how do we change the world? So I say to him, hey, I got this idea. Why don't we kind of create a device, and in that device we can put a virtual bug, a holodeck bug, right? It's like in Star Trek. I can pull it out of my pocket. Simply a bunch of cardboard. I can actually pull out this really cool 3D thing. So, engineer shows up and says, I built a spinning LCD thing that generates an image of a bug. Unfortunately, it takes up too much power. And unfortunately, it's not going to work. It works for about 10 seconds, the batteries run out, people get upset, parents don't buy it because the batteries are expensive. But my designer says, hey, look, I can create a little device out of a cell phone. I can build a prototype. There's a prototype that actually works, and we can make virtual bugs that allow people to have on a low-cost, high-resolution TFT for cost of goods of $22, a device that allows you to fight bugs, connect them up, you can battle across screens, you can download them across the internet. And boy, this is a generation who loves the internet. Kids are going to love this. So the bugs are flat, and this is really important for a 5-year-old, lots of green goo. When they fight, the heads get ripped off. The bodies, limbs, parts fly. So there's goo all over the screen. Right? This will sell, and it'll sell really well because schools will ban it. Mothers will hate it. Little boys will love it. Okay, so now I'm saying, all right, this will change the world. Mattel is all about plastic. Hasbro is about plastic. Electronic Arts is about video games. Can we make big problems for that little kids? How do we make little kids come together? Right? Internet's bad. The internet takes them apart. They sit in front of their screens. They end up like, you know, those people in conference rooms who play on the Blackberries, even though they're all in the same room. So, we can physically have them hook it up. And so I'll give them a little money to actually build a prototype. This team then takes the idea, builds 2 or 3 prototypes, then makes people touch the prototype, and play with the prototype, which is fundamentally ask a bunch of kids in the inner city if they like the toy. And go back and forth, back and forth, back and forth. And this is really important. Speed is everything, right? Speed is life. Fighter pilots, it's kind of an OODA loop here. If I can out-iterate my competition, I can move quickly, go through lots of design iterations. The most important thing is get to the working prototype as fast as you possibly can. It doesn't have to be perfect. It has to be good enough. But to get to perfection, you have to iterate. You have to iterate really, really fast. If you're successful, right, you have to be able to position your new idea and articulate your idea in the marketplace. And this is what I call the sharp knife theory. Okay? What do you do as a small company competing against a big company when you have a little idea that you want to make a big idea and they can outspend you, outmarket you, outsell you, and crush you out of existence? So what I believe you have to do is create a really sharp knife. You look for an idea in a place that they're lazy, look for a marketplace, so you have a bunch of lazy competitors, big competitors, typically worth billions of dollars, and you sit around all day, going to the street corner at 5 o'clock, beat on each other, and then at 6 o'clock they'll all have a beer. Build yourself something that's a sharp knife and throw yourself into the middle of the street. If everybody runs to the knife because they're afraid that the other guy will grab the knife and cut their throat, the guy's got a really innovative product. If you throw your knife on the middle of the street and nobody cares, nobody cares. Now, there's one part of the design aspect I think is really, really important that most people miss. Design is about forecasting the future and working your way backwards. The problem with most VCs is they're unable to do this. And the problem with a lot of engineers is they don't understand there is a process that you need to go through to change the world. So here's a little exercise I forecast the world 5 years from now. I come up with these alternative futures. And I imagine a piece of technology or a thing and how it affects, in that story, how it affects the world. Like, how will 5-year-olds play together 5 years from now? Not how they play today, how they'll play 5 years from now. When I'm thinking, when I was at the agency, how we're going to fight wars, I'm not thinking about how we're fighting today's war. I'm thinking about 10 years from now, 20 years from now. How are we going to fight that war? What do we need? And where do I go back? As I started with my inspiration, I go back to television or things I were interested in when I was 5 years old. When we do a story in science fiction or in fiction, and we put a piece of technology in the story, because I got to tell the story in my 1 hour segment or less, or 2 hours if it's a movie. It's a way for me to bridge the story, to solve an unsolvable or improbable problem. And that technology is the technology that I look for. So when I took over Intel, the first thing I told my entire staff to do was go watch television. Go read science fiction. And come back. Anything that was useful to solve the crime, to figure out where the bad guys were, The answer was in one of those stores. So now think about it. The cell phone, we communicate, right? The computer, the internet, right? Things that capture your imagination is about capturing the heart, the brainstem. It's an emotional answer. It's all about emotion. Design is great emotion. Engineering is making the improbable possible. And the more improbable the challenges that you make possible, the more money. So that's how the venture capitalist, at least this venture capitalist, thinks about innovation.
Wow. This is amazing. Gentlemen, you're not done yet. You're not done yet. The way this debate goes now is you've had your 6 minutes, and now it's an opportunity for our two panelists to ask any questions that they might have about this model, compare it to their own. Do you, Steve and Missy, do you have questions you want to start? Because I have some if you want me to start. Or go ahead.
I don't know. Do you have something you want to ask?
I can ask one, but you can.
Ladies first.
So, Gilman, I'm totally fascinated with this process because actually I didn't realize it was so much cognitive overhead for you as a venture capitalist to engage in so many of these decisions. And I know that you don't have that much capacity to do that for every single person that comes into your office to give you an idea. So can you tell me the top 3 things that people might say or do so you weed them out?
Okay, so I'll give you the top 3 things to do to guarantee that you won't get money from me. Right? So the first thing you should say is, you know, this is just like a case study. You get all the ideation show from both Harvard and Stanford. So if it's a reference to a case study, right? It's just like in Crown, Cork, and Seal. You're out. Never gonna give you a nickel. Second thing is entrepreneur shows up and says, you know, I have this really, really great idea. If only somebody would fund me, right? Any great entrepreneur worth her salt understands that funding is about giving the venture capitalists an opportunity to make a lot of money in their idea. They're going to build it no matter what. If you are totally sure of your idea, you will mortgage your house, in my case, mortgage my parents' house. I would scrape, I would convince people to work for me for nothing, because the vision is big, and we're going to figure it out. It's about giving this person the opportunity to make large sum of money, not asking for permission. And the third thing is, I hate is the feature. Somebody has a feature, and they think a feature equals a company. And that could be a feature like, this is a really good piece of good science, or this is a really cool piece of technology, but it doesn't change the world. And if they can't draw that connection to real people using their technology in a way that makes business sense, it doesn't even have to be a clear vision, but directionally correct. We're looking for. So if you kind of come on and say, this is great technology, and you say, I don't really care about business, I'll say, great, you know, call NSF, call DARPA. Here's the professor who would love to work with you on your project, but you're not going to get it.
All right. So having been one of those entrepreneurs who's been, I think at this point, probably about maybe 5,000 presentations with VCs. I mean, it's hard to believe that's been that many, but I mean, it's over 25 years. And having actually closed funding, I would say a handful of times. One of the things that I've seen that's difficult because of the nature of the work I do is that when you have an idea that's a compelling solution to a problem, but you don't know whether it will work. You think it might, but you're not sure because the technology is too far behind the horizon. But if it does work, there's a huge payoff, okay? But then again, it may be worth 0. I have found that the existing venture capital metrics that the risk profile that they follow, they will go and say, we can't go and quantify the risk. And so therefore, they haven't been able to fund many things.
Here's the problem. Look, investing is a portfolio strategy. So it's not about looking at each individual deal and taking risk out of the deal to make your bets. If the deal doesn't have risk, you can't make any money. Because the moment you start solving that problem, that obvious, not risky problem, easy slam dunk, put the ball through the hoop, anybody can do it, everybody does it. And you got 50 million startups doing exactly the same thing and making exactly no money. Okay, so that's a bad strategy. So what are you supposed to do? The way I look at it is like this. I say this often. I say a good venture capitalist takes the high-risk bets, and there's a way to take a high-risk bet. You look for low probability, high payoff. Things that most likely, in all rational ways of thinking by any normal person, probably cannot solve that problem. And then it's a person bet. I'll look at a person like Steve and I said, you know what? Nobody else can kind of solve this problem, but I think you have about a 15% chance of pulling this puppy off.
Just 15?
That's twice as good what I can typical. But that's okay. I got 20 bets to find one to do, right, in my portfolio. And that's the way I look at it. So I don't care if 19 bets fail, because when you fail, you lose 1x. If you get 1,000x return, I can lose a lot of x's to find that one big one. But if you immediately filter on the safe, low-risk bet, you never, ever get to the high payoff. So here's what I'm looking for. I say to you, my job is not to find the answer. My job is to believe that you can figure out to weave that little thread through that really narrow hole to find a solution that nobody else can solve. And that's the person bet in investing. You have to bet on the people, not just on technology. You have to be based in technology. You got to understand, you don't bet on things that have a 0 probability, but you like the ones close to 0. Because the ones close to 0 have the biggest payoff. And so the way I look at it is, I'm a NASCAR driver. And I've been racing along. There's a car accident. And it's just a big pile right in front of the car. It's flashing. There's smoke. There's fire. Things are spinning around. Now, what do? Now, some people say you accelerate. That's kind of a dumb idea. Right. Some people say slam on the brakes. The problem with slamming on the brakes is you lose control. You lose control of your car the moment you slam on the brakes. Other people say you look at the accident. Unfortunately, if you look at the accident, your hands go over where you look and you crash right into the big pile. There's only one way an entrepreneur makes it through. That is to look for daylight. Keep your eyes on daylight. Your hands will follow where you're looking at, and your car will go to safety. So my bet on Steve, in that case, is does Steve know what daylight looks like? If he knows what daylight looks like, he can explain to me what daylight looks like. What does the world 5 years look like with your product or service enabled? What will people do with it? If he can say, this is how I think people will use it, not how we can make tons of money, but this is how I think people will use it, if he can express that, if I have confidence in that person, and I'll do all my background checks, because I used to be with the CIA.
That's why you did it best.
Perfect. Gilman, thank you so much. Gilman, forgive me, but I'm about to do this. All right, Missy. Can you show us what design thinking is?
I will show you what my design thinking is, although I'm just so flattered that Dan did the boards for me, because as anybody knows who's a professor ahead of you never cleans his own board. So before I get going with my sketching, I wanted to kind of give you a little bit of background so you understand my perspective, which is a little bit different from the other two gentlemen here today. My specialty is something called supervisory control design, which means I design high-risk information systems for human interaction with complex technologies, i.e. cockpits, nuclear reactor control rooms, process control rooms. And so while you heard before that money was really, really important, money is at the root of everything, but I'm actually going to tell you for my kinds of designs, money is actually smaller than I think the overall goal of safety and mission accomplishment. And that's actually going to come out in some of my design recommendations that we're going to talk about. Okay, so if I was going to, now I'm going to be really academic here, and I really apologize that I'm the only academic up here, so somebody had to do this. I'm going to actually do the little Venn diagram here of design as I see it, where most of you are familiar with these little, usually you see them as circles, these shapes, but I'm going to have a little bit different today. And I was a little worried that my drawing would be really too bad for you to see, but after Gilman, I feel a little better that I'm not the only one that you don't want to play Pictionary with. Okay, this is really careful. My students always laugh at me too. All right, so up here at the very top, analyze. For most of you who've done any kind of design theory research, analyze is always at the top of the list. How we can't get to a good design unless we analyze. And in fact, I'm going to tell you, I cannot emphasize this enough. If I could bold this and make it jump out of the board and flash at you, I would. Because the most important part of design, I think, is analyzing the system, be it a technology or even more importantly, the socio-technical system that you want to put this technology in. For example, if you don't know what 5-year-olds like, then how are you going to know this kind of medium that you want to put it in? So when I say analyze, there's actually a very clear deliverable in my designs that comes out of this. And it's something, for a lack of a better acronym, we call FIR, which is functional and information requirements. Requirements, requirements, requirements. I mean, it's not something we've heard really yet, but from a systems engineering standpoint, certainly from a design standpoint, you cannot get enough requirements to start your system design with. So I'm really going to say, you must analyze because you must, for the purposes of my system, these information requirements are critical. They are the pieces of information, be it visual or oral or even tactile, that humans need to be able to have to make a critical decision. Do I need to put the rods into the reactor? Do I need to separate those two aircraft? Should I press this button right now to drop this bomb? Now, once we get our requirements done, then we come over here to the design block. And I'm trying to color this in black, and I really like what Gilman said before, because I'm going to say design is actually a black box. I cannot tell you how many companies, small and big, come to me wanting me to help them design the automatic interface design software package, where you type in, I want to build a nuclear reactor command and control facility, and I'm going to press a few buttons in a Microsoft Word format, and what's going to pop out is the automatic optimal set of design panels. And the good news is that if that ever happens, I hope I'm dead, and then I would be out of a job. But I really don't think it's even possible. Design is fundamentally, when you actually are in the act of designing, very, very creative. And even at MIT, in a very engineering numbers world, I really stress to my students that they have to really kind of step out of the box. And one of the things that I like to tell my students to do is, this is actually going to sound a little silly, but I actually tell them to go for a walk. We do a lot of really tough designs. When you're actually trying to figure out how to represent complex relationships like optimization functions or lots of processes all coming together that are interdependent in 3 spatial dimensions, including the time dimension, it is not easy to visually represent these things in pictures. And Dan has shown in his book, this design we came up with, these baddies, these moving arms. All the great design ideas I've ever had, and my students will actually agree too, they never came from sitting in a room, they never came from sitting around a blackboard, they never came from a bunch of sticky notes. All the really great design ideas that people in my lab have had when we've been out moving our bodies through space. And actually, sometimes I take my students out and we go walking around the Charles River, if you've ever been to MIT. I really do believe, this is a little philosophical, that you must get that blood flowing, and you need to get your brain in some kind of free spin to have those really good, novel, revolutionary ideas, because if you just sit in a room on your butt, you're just going to have the same ideas that everybody else has. Now, one thing I want to say, though, which kind of goes against the grain of the conference, which something about the word cool came into your informal conference slogan, and this also kind of goes against what Gilman and Steve are probably going to talk about, and I'm going to tell you about danger, Will Robinson. There's one really danger area in design that I see in specific context of the supervisor control systems that I design, and that is what I call the cool factor. So my students have to be aware of the cool factor. What is the cool factor? The number one display that I see abused in supervisory control systems are three-dimensional displays. Now, three-dimensional displays are really cool, and they're sexy, and they're fun to look at, and when you actually start to see things spin and rotate, that's very cool. Now, if I was an entrepreneur coming to Gilman and I wanted to design some kind of cool video game that wanted to make people buy that game, and they just wanted to play with it on a Friday night with their friends, 3D displays might be a good way to do it. But it turns out if I want to sell a 3D display to do air traffic control with, this turns out to be not only not a good idea, but an incredibly bad idea, because for the nature of that task, for precise judgments, and the FAA will tell you this, that they have spent nearly $1 billion trying to build 3D displays to do air traffic control, and it failed. It failed because even though the human brain, we think some ways in 3D for complex spatial resolution with closing, varying, decreasing range problems, we do not think in 3D, and we actually think better with 2D displays. So there are all kinds of examples I could give you about the cool factor, but you know, I didn't give it a circle slash. I didn't say no cool factor. I would be a hypocrite. For those of you who've been paying attention, a couple weeks ago I had all this media on Wired.com and everything because I succumbed to the cool factor and we're flying UAVs with iPhones in my lab. Okay, I'm guilty. You know, I like cool things too, and in fact, but I actually think this cool factor, flying UAVs from an iPhone for dismounted soldiers and or for people who just, you know, want to see what's going on around the corner, this is actually a really good idea. A little bit of a cool factor, but we're going to work that out through, okay, so we went from analyze design, now we're over to testing. As a design experiment, I tell you a big heavy sigh. I see this abused the most in academia and industry. In fact, I can't decide whose words about the inappropriate testing and evaluation strategies. For everybody who designs, theoretically you design because you have some question you want to answer. Is my design good? Is it bad? Is it usable? Does it help nuclear power plant operators not make the core go critical? And then there are metrics that help you answer that question. But most of the time, it is as if these two never meet. I have a hard time understanding if a lot of industry, the industry response to test is, I'm just going to measure everything and then somehow make sense of what I measure. But what happens is, this is where money does kind of come into play. If you measure everything, you don't have time or the resources or even the money to actually try to make sense of everything that you measure. And in most cases, you don't even know what question you answered in the first place. And I think this goes back to what Gilman is saying. This is where the engineers that try to be entrepreneurs kind of don't get it, right? They're going to spit at you a bunch of numbers. Oh, it has this and it does that, and very numerical responses. But in fact, did it actually answer a question, which you don't even really know if that question is good or not, unless you can connect it back to your information requirements. And so that kind of completes the loop. And what the last thing I have inside the middle here is test and model. Academics, we love to do models and we build test beds, but I actually think that this is kind of important because this is the cloud inside of here where you can do rapid prototyping. We do a lot of our design prototyping in some of these test bed and models so that we can save money, go do rapid prototyping in terms of time, get faster prototypes before we called Wired and let them know what we've done. Although we didn't really do that in this case. I actually finally hit on you know, just how to get publicity over this. We basically did this. We started flying UAVs with iPhones in 5 or 6 weeks. We did no testing. We didn't do any of this. Basically, we just did this, and it was cool and sexy enough that the media picked it up. So, you know, I'm a hypocrite.
I'm sure you must have some questions.
Sure. So I've always been run up against the wall on the functional specification design requirements, particularly by the professor. I'll give you a good example. When I did my game, a bunch of Air Force pilots came to me and said, we love this game so much, that here's a -1 and here's a -34, can you make these adjustments, which I did. And then I teamed with General Dynamics, and then we competed against a bunch of other companies who won a contract. And a bunch of requirements came back from DoD saying that fundamentally it had to be written in Ada, you know, it had to comply with this sort of requirement, and what they were designing was the next iteration of what they already had. And we're not willing to make the leap. The question to you is, how do you put together a good functional design spec versus the god-awful ones that get in the way of it?
Yeah, and this is a good question, and certainly the DoD would be the anti-innovation area in a lot of ways because of this problem. There's been a change in the past 10 to 15 years about the way requirements have been generated by the Department of Defense. In the old days, it was the Department of Defense's job to generate those requirements, and because of that, you got these very antiquated, outdated, yesterday's technology that they were doing requests for proposals for. But a recent change has been the DoD is trying to push the requirements generation onto the actual OEMs, the original equipment manufacturers, so that theoretically they can go to the cutting edge and then develop the functional requirements. Now, theoretically, that's one suggested improvement, and theoretically it should be better, although what we have are the guys who were in the government that retired, then they do double dipping, and then they move over to Boeing to do the requirements for the government, and so it's actually the same group of people still writing the requirements, you don't really have any major improvements. That is probably, to me, the most frustrating problem. I was an engineer for the government. That's actually why I got out and went into academia, because I found it so frustrating that I could not get past this very archaic system. Now, the real solution to this problem is finding the right warfighter in the field who likes your technology. And this, to me, is it is very strange because it wasn't really the way when I was in the military, the way business is done, but it is the way that business is done now. If some theater commander wants your technology, like a iRobot robot, or some new Predator, or some new something, if somebody in the field makes the call and says, I want Gilman's X, then they will get X. They will go through all these changes and get X to happen. So this is this decentralized world that things like the internet and flying UAVs through iPhones and YouTube, and that's one of the great things about the connectedness of our environment is now that warfighters in the field are finding out about these technologies. And so I think we're on the cusp of this new acquisition strategy where you do have a customer base, and that customer base are the warfighters in the field. You get the right flag level, high level officer to notice your technology, and then it works.
So one of the things that you pointed out is the design box, the black box, and you got to let the juices flow, the creative juices flow. But the other thing I saw in your diagram that I didn't quite see you touch on was after you go to analyze the design, then from design to test, I think you have another arrow that goes back up. And the question is it ever the case that after you've done the test and the design of the test, that you change from what you've learned the functional informational requirements?
Yeah, and so I'm sorry I didn't make that. Yes, absolutely, you go through there. Nobody ever, I would bet my life on it, gets their first round of functional information requirements correct. You never do. You can make a really good stab at it, but it's really often not until you get into the field where you actually can see how these technologies will occur. And I have one really great example is the Army, going back to the cool factor example. Somebody sold the Army on spatial audio, very cool, where you put on a headset and you actually can hemispherically pump in sounds, and the idea was that unmanned vehicle operators would be able to understand if there was a pop-up target on the right side and a pop-up target on the left side, they would actually be able to react faster and more appropriately, getting the right weapon systems on the target hemispherically. So they did all this research in the lab, millions of dollars of development in simulators and testing in the simulators, and it was a beautiful project in the research lab. This is going to revolutionize the way UAVs work. And then they put it in the real field setting with real Army operators. And can anybody guess what happened with and there's always two guys in the back of a trailer in Army UAV operations. So can anybody guess what happened when they put those headphones on? They went like this with them. Because the two guys needed to be able to sit and talk to each other. And not once did anybody, all the researchers, human factors engineers, people who I work with all the time, they didn't do a good requirements analysis. They got all the way through there, wasted a lot of money, only to come back to find out that they missed an important requirement, which was that the operators needed to be able to talk to one another.
Wow. Missy, thank you. It's true, because every movie you've ever seen, this person takes one of the earphones off and puts it right up here, right? All right. Benjamin Button. Oh, hold on. Let me do my task.
By the way, in business, no one cleans whiteboards, so don't feel bad. You know, the thing I was very impressed with, I came here, all the pens were functional. Now, if someone can invent a system which will guarantee that you have a pen that can actually write on a whiteboard when you enter a conference room, I think you should invest in them, because, you know, we're going to take over the world. All right. So, I come from a little different place than Gilman and Missy. In some ways, I'm a little bit in between. I am an entrepreneur, but the kind of things I tend to do are very early stage things. Ideas that are, you know, at this point, not even sure whether or not it's possible to come up with a solution. And then what I do is try to figure out a way to go and get these things to work. And at that point, we go and only then know how big the market could really be. So the challenge that I want to talk about was specifically a challenge that we faced that turned out to be a very, very clean way to explain the process that we use for just about everything that we develop. When I say we, it's myself, and I always do things collaboratively, both with other individuals, with academia, with venture capitalists, with large corporations, etc. So the problem that we were facing was that in movies and in computer-generated games, there was a need to capture human faces in 3 dimensions, so that you could then either create a person that looks exactly like the person that you're capturing, say it was a famous actor. You can see there where they did it with Tom Hanks for the Polar Express on the left. Or to take a character and change that character into a different person. For example, make the person older, or turn them into a creature like Gollum in The Lord of the Rings. And the technology that had been used for really about 20 years before we had started this problem is called marker-based technologies. You can see little dots on Tom Hanks' face. You see those little dots there? And they got up to the point where they would capture maybe 200 of these little dots. And then you have cameras all around, and the cameras go and triangulate on the dots. And from there, they figure out where in X, Y, and Z space the dots are. X, Y, and Z space the dots are. And from then, there it creates a 3D model. Here's the problem we faced. Those dots were great if you're capturing a skeletal part of the body, some rigid part of the body. But it was not good for a deformable surface like a face. And it was even worse than that. The human brain is wired for faces. We have a from the point we are born, we are attuned to notice subtle details in the way the eyes move, the lips move, the cheeks, the lips, the expansion of the nostrils, etc. So these dots were measuring things on the order of, here I am talking, I should be drawing. We were measuring things on the face. Here's a face. On the order of centimeters. Okay? And what we realized is that we were going to have to measure things on the order of tenths of millimeters. Okay? So you can imagine the problem of trying to put that many dots in someone's face. It's just not practical. And on top of that, as the face compresses, the little dots bump into each other, or even if you're drawing it, they overlap. So there was no solution. And in fact, people tried very hard to make some movies using just the dots to see how good the computer faces were, and perhaps used animators to make it better. In the next slide, you can see what the problem was. It ended up with something called the uncanny valley. Now, this is actually something observed way back in 1970, which is that we like the way faces look as they get more and more realistic, as from a representational face, all the way up to, say, Princess Fiona in Shrek. And each time you ask the person, how does this look, they'll say it's better and better. All the way up to the point where a face looks almost like a human face. And unless that face is absolutely perfect, what will happen is you'll go and think that, oh my goodness, that's a person, but they maybe are sick, they have a disease or something like that. And it's unpleasant to look at. And so you actually get a negative reaction, and there were several movies made where people had that negative reaction, and it turned people away, all right? So we realized that, okay, we're gonna have to do a lot better than that current marker-based thing in order to get past the uncanny valley, where we can create a computer-generated face which is subtle enough to actually look like a real person. Now, this, like everything else we faced, was an I've developed over the years, you know, a QuickTime web TV, whatever it is, wireless technologies. I started out by saying, okay, in order to invent something, the more difficult problem I've always faced is not finding an answer. The more difficult problem I face, and this has been echoed in the last two talks that you've heard, is formulating the question, all right? And basically, the question that people were asking up till then with motion capture was, how can I take what is basically a random, you know, structure, which is a human face, and add structure to it in one form or another. So I take a human face, and I'm going to put dots at regular intervals. And there are other people that put lines, you know, crossing at regular intervals and so forth. And by adding structure, from there, a computer is going to see in 3D. Okay, it's going to capture a face in 3D. And that just didn't work. It looked really bad. So I said, okay, we've got to figure out another way. We had no idea how to do it. We didn't know anything about motion capture. So what we did was, we, in our offices at Reardon, we actually have 3 banks of whiteboards that go up and down. So I outdid you guys by 1. But anyways, and what we do is, when we start an idea, we throw them up on the board. In the case of what the technology we developed, which is called Mobile Contour, we actually started about 25 ideas. And everything people can think of. Just like Missy was saying, you go out, take a walk. You go out, think about things in a different way. Just think out of the box. We said, instead of putting dots in the face, suppose we did ultrasound, like the way they look at a baby in the womb. Okay? Or maybe we'll go and measure the time of light as it's making it to its face and comes back. Maybe we'll go and use create a 3-dimensional mask with slots on it that is a stencil, and then use an airbrush to blow a pattern into it that's very, very regular. Maybe we'll go and bury the face in a liquid or a gel or something like that. We went through all these different things. And every one of these ideas, sometimes we could figure out this was a dumb idea right in the beginning. Other ones we explored for a little bit. And other ones, and so on. And when we explore them, we hit a dead end and say it doesn't work. All right? And then finally, what we had is one idea, in this case, drawing the lines through the mask, that turned out to be like something that would lead to something. We're getting some sort of results that look pretty good. So we took that idea and then began to try different variations on it. And every one of these things also led to a dead end. And what's going on now is this, over a course of a couple of years already, has gone by. But what happened during one of these experiments, when we were using an airbrush to blow through this stencil in a mask, we found as the cameras were trying to correlate on these lines that we were drawing, they weren't correlating very well the lines, but in the spray that was spilling out from the stencil, making a random pattern, the cameras would lock onto it. They would lock onto the randomness around the lines. So that gave us a key insight, because the key insight wasn't the solution, but we had done another idea we had, was trying to go and correlate the pores in the human face. You know, the randomness of the pores, and use that. But the pores were too small for the camera optics. And besides that, actresses, for example, would make their faces very, very smooth. We could not capture them. But we thought if we took that idea and then combined it with another idea, which is putting on a type of phosphorescent makeup, which could cause it to glow and emit light. And then we went and took a sponge, and we sponged the face to make a complete random pattern. So everything, we went, instead of going this way, which is adding structure, we went from this way and made it consistently random. So now we had a face which just had, you know, random dots all over the place. And instead of taking 2 hours of prep, it actually took 5 minutes. Okay? And then, using the correlation technology, that was it. It worked. We were capturing a face, and that was it. We were capturing a face with an accuracy of 1/10 of a millimeter. It blew us away. And it was so much simpler than the other ideas. Trouble is, it took a week of computation to capture one frame. Okay? Well, actually a few frames, just a week. And the lights were tens of thousands of dollars and so forth. So at this point, it was a matter of taking this idea and refining it. So this is the R part of R&D. Here's the D part. And so the D part then, we went and figured out better computational algorithms, and again tried a bunch of things, and then found one that worked. And then we had to come up with a better lighting system, which is the whole, what I call an adjunct invention. And we tried a bunch of different things, and we were using LEDs, and they were way too expensive. So finally, we took a conventional fluorescent bulb, you know, one of those ones you would just have at a hardware store. So these things were costing us around $10,000 each. These ones were costing about $2.50 each. And we designed an electric circuit which drove it, because no one had bothered looking at fluorescent lights in the last 50 years to design better circuits that could make this light flash in a microsecond. So we could flash this light as fast as an LED. So that combined with that, and then we came up with a new system for shuttering cameras and so forth, and it all combined into finally the moment contour system, which was a practical system. Didn't just work in the lab, but actually was inexpensive enough and was very convenient for actors and actresses and for the directors, and allowed us to make movies and video games.
And you won the Academy Award.
And well, the motion venture button movie and the special effects company that used this technology for it won an Academy Award. And almost everyone who has seen that movie does not know that, in fact, for more than half of the time Brad Pitt is on the screen, it is his performance that we captured, but it's a 3D character that's been generated. That's what we're going for.
Perfect. All right, we've got 5 minutes for a quick question from, or debate, or counterpoint from Gilman and from Missy. So we're about 5 minutes to go.
So how do you avoid climbing a tree to the moon? One of the challenges I've had with this strategy, though sometimes you get great results, is you get down these long paths where you're looking like you're making great progress pursuing a strategy, only to find that you're at the tip of the tree and you're not that close to it. And it requires you to do radical thinking. When in the process does intuition take over? When does the back of your, the hair in the back of your neck stand up and say,
What do we call this an endpoint, right? So what we do is we look at it and say, okay, you know, if we go and take this thing out to its logical conclusion, is it going to be too expensive? Is it going to take too hard to use? It's going to be uncomfortable. Is it unsafe? Are the materials we're using? We had some materials that, if they got in your eye, would be dangerous for the actor, so we rejected those. Okay? So anything we can do, we try to find things that don't work. Those are our favorite things that we try to prove they can't work. It's the biggest thing we do. Prove it doesn't work. Prove it. In fact, I proved that didn't work and I was wrong. Okay? I proved that didn't work and I was wrong too. Turns out we were just thinking about it the wrong way. But it took us to do something we thought was going to work in order to do it. But at some point, we have ideas we've tried, and we're still working on it. We do not have it. We're working on a new lens, for example, and we haven't finished it. But there's other things we've worked on that we have gotten to.
I really don't have any questions.
Well, we're perfect then, because I was just informed that we've got to cap this off right now. So let me do a very, very quick thank you, because I find this fascinating, again, to be able to see 3 completely different points of view coming from people who are of the same background as all of us in the room, or very different backgrounds, all trying to address the same problems and come up with different ways of doing it. And the thing that to me is always gratifying is to realize, try to imagine what we just went through for the last 45 minutes if people had not been able to draw the pictures when they tried to talk. It's an amazing thing that happens, why we don't give more emphasis and more ability and more training on how to go ahead and just draw the picture. And I've got to tell you one thing, that in talking with each one of the panelists, when the word first went out what we were going to do, the pictures came back to me and every one of them said, I won't draw. And then we got on the phone and talked. And I don't know what it was, but in the process of just having a conversation to realize that everybody came to realize that it is the act. I will be willing to draw. And I'm glad you did, because the drawings that you did now are orders of magnitude better than the drawings that had been sent through in the PowerPoint, because we saw you create them. So with that, I want to thank you very much for your time, and thanks everyone again for inviting us to come in and do this panel, and I hope you found it useful. So thank you all very much.
For more, please visit us at stanford.edu.